Okay, I think we can start. So, hello everyone, I am Marcell Juhasz. Welcome to my presentation about the cost of abstractions in embedded systems. Let's start with a brief introduction about myself. So earlier this year I graduated with a master's degree from the Vienna University of Technology. And I have been working with C++ for over 6 years now, with a main focus on embedded systems in the last couple of years. My primary interest lies in applying C++ in resource-constrained environments. And here you can see my contact information, and if you find this presentation interesting, then the whole project that led to it is available on my GitHub, so feel free to check it out. I work at CppCon Engineering as an embedded software developer. We are a global innovative service provider. We transform the ideas of our clients into business models and products. So if you need help with any project, or if you're just simply interested in collaboration, then here is our contact information as well. Feel free to contact us. So, what was my motivation for doing this research and for preparing this talk? Since this is a C++ conference, most of you will probably agree with me when I say that C++ offers a lot of powerful and versatile features. There are some that we as embedded developers could not really live without. There are others that we are not really allowed to use. And then there are a bunch of other features, some of which are often debated in the community. Everybody has their own opinion, and some people say that C is as efficient as it gets, and that C++ comes with inherent runtime overhead caused by the abstractions. And there are people that say the exact opposite. So sometimes it is hard to decide which features we are allowed to use and which ones we should avoid. So to clear up the misconceptions, I went ahead and investigated the topic, and I gained valuable insights by doing this research, and I hope that this presentation will provide you with some valuable knowledge as well. If we are talking about embedded systems, then one thing is clear, that one of the most important factors is overhead. Overhead in terms of memory usage and runtime performance, as both the available memory and execution times can be limited resources. So first and foremost, it is important to clarify that the topic will be discussed from an embedded systems point of view. So I wanted to go as low level with C++ as possible, and I wanted to analyze the effects of abstractions as close to the hardware as possible. So for that reason, I will primarily be focusing on the hardware abstraction layer, as this is the layer that interacts directly with the microcontroller. We will see how a traditional hardware abstraction layer is implemented. We will find suitable places for the abstractions to be integrated in the code base, and then we will analyze their effects at the lowest levels possible. We will primarily look at encapsulation, inheritance, and polymorphism, but we will also identify the inefficiencies present in the current hardware abstraction layer implementations, and we will see methods that can help us to deal with these inefficiencies by leveraging some of C++'s more advanced features. I would also like to talk to you a little bit about the methodology, so the setup, the workflow, and the metrics of the measurements that I used to put together this presentation. It's probably not a surprise to you that I started out with the source code. I implemented some functionality in C using the provided hardware abstraction layer, and then I introduced C++ abstractions to the code base, while keeping the functionality, of course. I cross-compiled the projects for an STM32 microcontroller. I optimized for size, as it is often a limited resource. In this step, I could also measure the compilation time as well, and assessing the size of the binary of a compiled project is pretty straightforward. Then, on one hand, I went ahead and I analyzed the disassembled binary. I wanted to see what actually gets executed on the microcontroller, and this way I could assess the runtime performance in an analytical way. And for getting empirical results, I flashed the target, I executed the firmware, and I measured the execution time on the target. Now, I will be primarily focusing on binary size and runtime performance, as these are the two resources that are often limited for certain embedded systems applications. There are devices with as low as 16 kilobytes of flash memory, or probably even lower. And as for runtime performance, there might exist some real-time constraints for certain projects, but even if such requirements are not explicitly stated, then still very often the shortest possible reaction time is still required. So before we jump into the main topic, I would like to just briefly introduce the concept of the base firmware. which will serve as a basis for comparison for both the binary size and the disassembled binary. So I simply define the base firmware as the absolute minimal embedded project consisting of nothing but a main function with an empty infinite loop. But embedded developers probably know that the main function is not really the entry point of a firmware application. So the first thing that gets executed is the startup script. This is usually written in assembly, and it is responsible for defining the vector table, for setting the stack pointer, copying data between flash and RAM, initializing global and static variables, calling static constructors, and then eventually calling the main function. The third important piece of the puzzle for a base firmware is the linker script, which basically just specifies the memory layout of the application. Now, as you can see, there are a couple of things that are happening even before the main function is called, and even so, with an empty main function that basically does nothing, we are already around 2 kilobytes in binary size for both C and C++. So before we can start and build layers of abstractions, we need to find a suitable place for the abstractions to be meaningfully integrated in the code base. For that, I would like to just briefly introduce you how the current hardware abstraction layer is implemented. So just to summarize it briefly, the hardware abstraction layer provides data structures, and we as developers can instantiate and populate these data structures according to the necessary configurations that we want to apply. And then we can use these populated data structures to call the functions of the hardware abstraction layer. And these functions take our input parameters, they do some validation, and then they branch off to execute the necessary computations. And one of the most important things that the hardware abstraction layer does for us is that it abstracts the complexity of the required register operations. So as you can see, a hardware abstraction layer is full of such register operations, and for every register operation, the hardware abstraction layer calculates some kind of a bit mask to clear or set bits in the registers. So now that we have an idea of what we are dealing with, let's jump right into the main topic of the presentation, building layers of abstractions. Now, as we have seen before, the hardware abstraction layer is full of such register operations. And if we look at this register operation, we can identify at least 2 places where abstractions can be meaningfully integrated. If you look at this part of the register operation, we can see that this is the generic part. It simply handles the bit manipulation of every register, independent of its type. And then if we look at the second part of the register operation, this is the register-specific part. This is the one that handles the bit mask calculation for the register operations. And this part must know the meaning of every bit in the register. And it also must or should provide meaningful member functions to interact with the underlying register. So if we want to analyze the effects of an abstraction, one key factor is that we want to modify as little of the original code base as possible. So keep the original code base untouched, and then introduce the abstractions in as little code change as possible. So let's start with encapsulation, meaning classes. We have seen in the previous slide with the register operations that there are the generic register operation part and the register-specific part, both of which we can meaningfully encapsulate. So represented as a UML diagram, the class hierarchy would look something like this. It's just an overview. There is this C-register class, which implements the common generic register behaviors. And then there are these register-specific classes which implement the unique register-specific behaviors. Now, I want to show you just swiftly an implementation. It's a simple example implementation so that we all understand what I mean here. Let's start with the C-register class. As I have said, this is the class for the basic register operations. Every register is mapped into memory, so every register must have an address in memory so that they can be accessed via simple memory access operation. In this case, this is solved with a private member variable to an unsigned integer. So this is the class that implements the generic register behavior. So this provides member functions that allow us to interact with every register in a common way. So for example, setting the whole register, reading the register, setting only parts of the register selected by a bit mask, and so on. Now, as for the register-specific classes, these are the ones that are responsible for the unique register-specific behaviors, so they need to be able to calculate the necessary bit masks for the register operations. They are still registers. They need to have access to the generic register operations, because in the end, they will have to read and modify the value of the register. Now, it probably already occurred to you that this would be the textbook case for inheritance, but remember that we want to analyze the effects of abstractions in isolation, and we start off with encapsulation. So, yeah. As I've said, this class needs to provide ways to calculate the necessary bit masks, and in this case, these are just simply encapsulated in some private member functions. And as for the interface, this class also must provide a clear interface for interacting with the underlying hardware. So for example, in this case, calling the set mode with the corresponding enum value will provide a much more clearer and understandable implementation than just to shift bits around in the code somewhere. As you can see, if we apply all of these changes to the code base, we already arrive to a much clearer and more readable implementation. So it's pretty nice. Now, before I answer the main question about the runtime overhead of this abstraction, I also want to just briefly mention this side effect of encapsulating the register operations this way, because it makes it possible to test the firmware application on the host machine. Because as you have seen before, and you probably already know, the hardware abstraction layer is full of these register operations that we have just seen. They are all over the place, and they are accessing fixed memory locations. And you probably already know that desktop applications do not really like it when you access memory that is not yours. But when the register operations are encapsulated this way, then it makes it possible to simply replace the implementation of the C register class, because in this case, every access to the memory, to fixed memory locations, is handled in a centralized way by the C register class. So this makes it possible to simply replace the implementation, and I actually used this feature during this project when the analog-digital conversion cycle produced suspicious values. Then I could just simply replace the C register's implementation. It didn't access unknown memory anymore. It just logged which registers I was accessing, which bits I was setting or resetting. And this way I could swiftly find out which configuration steps I was missing. So it's really just a nice side effect. But back to the original question. So what price do we pay for this abstraction? The answer is nothing. It's free. It compiles to the same binary as did the C code without the abstractions. And I think that this is actually quite a good price to pay for all of the benefits that we have just gained, like readability, maintainability, and testability. Now, this is all nice and good, but for me, it makes more sense to have static member functions for the registers. So on one hand, the registers don't have internal states anyway. So from a technical point of view, it is possible. And my personal opinion is that this code is more readable, so that I don't have to instantiate the objects before calling the member functions. The implementation is straightforward. I just modified the member variables and the member functions to be static members. Now, when I compile this code, I noticed that there is a slight increase in binary size, and this slight increase does not seem much at first sight. But if you remember, at the beginning I told you that the base firmware's binary size was already around 2 kilobytes. So the difference in binary size increase is quite significant. So the question is, why did this happen? I went ahead and I analyzed the disassembled binary, and I found that a function with this prefix appeared in the binary. And of course, it makes sense if we think about it, because what we have just done is that we have made the C register objects static member variables of the specific register classes. This would mean that the C register objects now have static storage duration, which also means that their lifetime must begin before the main function and must end after the main function is returned. And consequently, there must exist some piece of code in the binary that is responsible for initializing these static objects, and this is exactly what this function does. I also must add that it wouldn't really affect the runtime performance, because it runs only once before the main function is even called, so it only increases the startup time, but at the same time it also introduced a slight binary increase, which might be not desirable. So The question is, can we get rid of this binary size increase while still keeping the static function calls? And the answer is yes, of course. One option that we have is to make the cRegister class a static or a templated class and pass the address of the register in memory as a template parameter. Now, if you think about it, it actually makes a lot of sense because the addresses of the registers are known at compile time. They are fixed and they do not change at runtime. So passing them as a compile time template parameter is definitely at least a choice to consider. Now, if I compile this code, the binary size returns to the original, and the disassembled binary looks the same as well. Now, one question that might occur to you, at least it occurred to me, is why did this actually help? Because the cRegister objects are still static members of the register of the specific register classes, so why don't they have to be initialized now like they had to be initialized before? And the answer to that is that if you remember, every register needs to know the memory address, of its own memory address. And in the first version, or in the previous version, we have solved this by adding a member variable. And although we have made this member variable a constant, we have to remember that const in C++ doesn't mean a compile time constant. So it's still a runtime constant. Even if it's undefined behavior, you can still change the value of a const variable at runtime. But when we are passing the address as a compile time template parameter, now the cRegister classes are fully defined at compile time, and simply the compiler can do a lot more optimizations for us. Okay, so we have looked at encapsulation. Let's see what inheritance brings to the table. So you already probably noticed, and I also mentioned it, that this would be the textbook case of inheritance. There is this cRegister class. It can be looked at as the base class. It implements the generic register behaviors. And these register-specific classes, these are still registers. They inherit the common register behaviors, but they also extend these behaviors with their own register-specific implementations. So the implementation itself is pretty straightforward. It is a simple inheritance. There is a base class, the cRegister class, and the specific register classes are the derived classes. Now, what's the price that we pay for inheritance? Again, it's nothing. Luckily, it still compiles to the same binary. And I was actually glad to see these results because when we are learning C++ at universities or at schools, we are often warned about the runtime overhead introduced by dynamic polymorphism. And since dynamic polymorphism requires inheritance, the associated overhead often could be mixed into with pure inheritance as well. But as demonstrated here, if you use inheritance on its own, then it doesn't introduce any runtime overhead. Okay, so let's talk about polymorphism. Polymorphism is a larger and more interesting topic when it is discussed from a runtime overhead point of view. So the encapsulation and inheritance could be successfully analyzed at the level of register operations. But for introducing polymorphism to the code base, I think that we have to move a little bit higher than that. So let's imagine this very common scenario where we have a printed circuit board. Somewhere on this PCB, there is a microcontroller, and there are a number of peripherals interfaced to this microcontroller. Now, in this case, our job as embedded developers is to implement the interface between the microcontroller and the peripherals, usually in form of a hardware module such as GPIOs, ADCs, or some kind of a communication bus. Now, one option that we have here is to use the hardware abstraction layer directly in our implementation. In this case, there is no separation between the two. And this also means that this external peripheral interface implementation is now dependent on the hardware abstraction layer. So if you wanted to port this piece of code between different devices of the same manufacturer, then it probably would be pretty simple because the interface of the hardware abstraction layer is kept consistent exactly for this reason. But problems will be rising pretty quickly if you want to port this code to another device of another manufacturer, because now you have to port the whole implementation of the external peripheral interface, and it can be very time-consuming for complex peripherals. Another way, another option that we have to solve this issue is to introduce some kind of an indirection to the code base. As you can see, in this case, the external peripheral interface doesn't use the hardware abstraction layer directly in the implementation anymore. So this also means that we have just made the external peripheral interface hardware independent. So this will make it easier to port the code between different devices of different manufacturers. And the first thing that probably pops into your minds when looking at this diagram is dynamic polymorphism. In dynamic polymorphism, we have interfaces. These are abstract classes with virtual functions. And if you want to port this code, then all you have to do is implement realizations for these interfaces. And through these realizations, then the external peripheral interface implementation can interact with the underlying hardware. So I think that this is the level where polymorphism starts to make sense. And this is also where I analyzed its effects. So let's look at it. Look at an example implementation. So as I've said before, we have interfaces such as this IPN interface. It encapsulates so it provides the necessary virtual functions for interacting with a simple GPIO. In this case, the set and the reset functions. The CLED class is the external peripheral interface that we have seen before. So probably an LED is the simplest device that you can interface to a microcontroller, but it will be sufficient for demonstration purposes. So as you can see here, the CLED class doesn't use the hardware abstraction layer directly into implementation. It interacts with the other underlying hardware through the IPN interface. The CPIN class is the realization of the IPN interface. So this is the piece of code that uses the hardware abstraction layer directly in the implementation. And this is also the piece of code that you would have to change if you wanted to port this whole project. It can be a lot less work than to port the whole external peripheral interface code base. Now, at this point, knowing what you're doing with your compiler and knowing what you're doing with your language becomes important as well, because as you can see, whether runtime type information is included in the binary or not, it makes quite a difference when it comes to binary size. You can use compiler flags to exclude the runtime type information. It is always best to read into the documentation of the compiler, because as for GCC, it states that if type ID and dynamic cast are not used, then runtime type information can be excluded, but it might be different for different compilers. Now, if we look at the version without runtime type information, we can see that it nearly compiles to the same binary as the original C code. There is a slight increase in binary size, so of course I went ahead and looked at what this difference is, and the only difference that I could find was that the set and the reset functions, so these are the implementations of the virtual functions, so the call to these functions are not inlined in the binary. And I was actually surprised to see these results, because when we are talking about dynamic polymorphism, we usually talk about the indirection introduced to the code base, so we are talking about virtual function calls, the virtual table, and such things. But these were actually nowhere to be found in the binary. So what happened to the promised overhead? And the answer is devirtualization. So you can also see in this code, but to summarize it briefly, devirtualization is the process when the compiler can decide statically at compile time which function it should be calling, so that it can produce a direct call to that function rather than a virtual function call. So in this case, also presented in this code snippet, both the CPIN and the CLED classes are statically allocated, so the compiler can do this optimization. I also must add that devirtualization works to a different degree for different compilers. So some compilers can do a deeper analysis of your code and resolve much more complex indirections. Other compilers simply cannot. So for that reason, I would also want to look at the overhead of dynamic polymorphism without devirtualization. So I want to look at the overhead of a virtual function call. Now, if you look at the disassembled binary, or if you look at the binary, we can find the implementation of the virtual functions somewhere in memory. So in this case, these are the set and the reset functions of the CPIN class. You can also probably guess it from the mangled names. And these functions simply reside at some location in memory. If we further analyze the binary, We can also find the virtual table in binary. So this virtual table is nothing magical. It's simply a block of memory somewhere in the binary, and it has the memory addresses of the virtual function implementations. So in this case, this is the virtual table of the cpin class. It has pointers to the cpin class's implementations of these virtual functions. Now let's look at the disassembled binary to analyze the overhead of a virtual function call. First, the address of the virtual table gets loaded into some register. And this is the point where we in the code passed the cpin pointer to the CLED class. Now, if we want to call a function through the interface, a virtual function through the interface, then the correct address of that function gets loaded from the virtual table. And if we have the correct address, then the execution simply jumps to this address, effectively calling the function. Now, I also must add that the set function doesn't have any input parameters, so there is no parameter passing in the binary. This will be the overhead of a pure virtual function call. And in and of itself, it doesn't seem much, but it will prevent a lot of compile time optimizations down the line. So do we have any other option to implement this kind of an indirection with C++? And luckily, yes. Modern C++ offers a new solution to deal with this problem. We can use concepts to implement interface-like structures. So these are not interfaces in the common sense anymore, but you can think of them as such. And you can think of the implementations that we give that satisfy these concepts. You can think of those as the realizations of the interfaces. And this kind of a relationship is often referred to as static polymorphism. I'm actually not sure if this is the proper terminology, but I will stick with static polymorphism for the time being. So let's look at the implementation. As I've said before, we can use concepts to define these interface-like structures. These are not interfaces in the common sense anymore. These are a set of requirements or constraints that you can apply on template parameters. So for example, in this case, the IPIN concept requires any type that wants to satisfy this concept to have the set and the reset functions defined as they are represented here. I also must add here that the requirements stated by concepts are not as strict as the requirements stated by virtual interfaces. So for example, here, this IPIN concept states that the type that wants to satisfy this constraint, it must have a set function. This set function must return void, and it must be callable without passing any argument. And this is the important part, because it doesn't state that the set function must take no input parameters. It states that it must be callable without passing any. So if you had the set function that would take an integer input parameter with a default value of 0, that would still satisfy this constraint because you can call it without passing any input parameters. And similarly, if you had a function here in the concept that would require a parameter of a 32-bit unsigned integer, for example, that function you can satisfy with another function that takes an 8-bit unsigned integer because there is an implicit conversion between the two. So I'm not sure if this is an advantage or disadvantage of this method, but it's just simply the way it is. Now, the cpin class, you can think of this as the realization of the IPIN interface, but what it actually is, it's simply a type that satisfies the requirements stated by the IPIN concept. So you can see that this cpin class has the set and the reset functions defined as the IPIN concept requires them. And with this additional static assert at the end, we can also explicitly state what we want to achieve here. Now the CLED class, this is our external peripheral interface. You can see that now it is a templated class, and it takes a type that satisfies the IPIN concept. So this piece of code will work for every type that satisfies the IPIN concept. And if you pass another type to this template that wouldn't satisfy these requirements, then you would get a clear and understandable compile time error message, and not these cryptic error messages that we are used to when dealing with templates. And you can also see, or maybe it's not that visible, but this code does not involve any runtime indirection anymore. So all of these relationships will be resolved at compile time. So what is the runtime overhead of this method? Luckily, it's nothing, so it compiles to the same binary as did the C code. And I actually really like this method because I think it has huge implications on how we write portable code for microcontrollers. So this would allow us to implement these external peripheral interfaces in a hardware-independent way with guaranteed zero runtime overhead. So it's really powerful. Now, we have talked about encapsulation, inheritance, and polymorphism. The next thing that I want to talk to you a little bit about is firmware architecture and why firmware architecture matters so close to the hardware. So far, we have investigated the effects of abstractions possibly in the hardware abstraction layer, but to tell you the truth, developers do not usually modify the hardware abstraction layer. So the hardware abstraction layer is taken as is, and C++ is introduced as a kind of a wrapper around the provided hardware abstraction layer, upon which we can then build further C++ firmware architecture. So this is a huge topic, so I don't want to go again into detail with binary analysis and code snippets. I want to approach this topic from a different direction, and I want to talk to you about why bad architectural decisions can lead to a lot of runtime overhead. So we have already discussed the effects of abstractions, and we have seen that they introduce very little to no runtime overhead to the code base. It wouldn't be different here as well. So for you to understand what I'm talking about, let's imagine this very common, or maybe not so common, but this scenario where we have a microcontroller and we have a 7-segment display interface to this microcontroller GPIOs. So if you wanted to change the number displayed on this 7-segment display, then you would have to update the bits in the output data register accordingly. If you are going for performance, then you would want to limit the number of register operations. So optimally, you would want to take a single bit mask to clear all of the necessary bits in the register, and then take another single bit mask to set the register to the desired value. Now, this is considered to be one register operation, and this is how the hardware abstraction layer actually handles these kinds of operations. But if we are thinking in terms of firmware architecture, then at first sight, at least, it would make sense to encapsulate the behavior of a single GPIO into this cpin class, because then it would provide us with a clear interface to set or reset the level of this of a single GPIO. But if we are going with this architectural decision, then we can only change the value of one pin at a time. So we take the first pin, we clear its respective bit in the register, and then we set it to the desired value. And then we move on to the next pin. Again, we clear the respective bit, and then we set it to the desired value. And we do this for every pin, one after the other. But as you have noticed, we have just used 8 register operations to achieve the same goal that we did before with a single register operation. And if we are thinking in terms of a wrapper around the hardware abstraction layer, then the case is even worse, because you have made 8 calls to the same hardware abstraction layer function. And this will introduce a lot of runtime overhead. Not to mention that between setting the first pin of the register or the first pin of the GPIO and setting the last pin of the GPIO, you have invalid values on your 7-segment display. Now, in this case, a much better architectural decision would be to operate on a port level or on a pin collection level, because again, this method will allow you to use a simple single register operation to achieve the same purpose again. The conclusion that I want to draw from this is runtime. So bad architectural decisions can lead to a much worse runtime overhead than abstractions would, and we are probably worried about the wrong thing when talking about the overhead introduced by abstractions. So in the last part of the presentation, I want to talk to you about the inefficiencies present in the current hardware abstraction layer implementation. So I want to identify these inefficiencies, and I want to show you methods that allow you to deal with these inefficiencies with some cool C++ features. So I've already presented this code to you at the beginning. It simply shows how a traditional hardware abstraction layer is implemented. As you can see, it is full of runtime computations. So on one hand, the input parameters are usually validated at the beginning of the functions, although from production code, this is also nearly always optimized out. And it takes our input parameters and it branches off to do the necessary register operations. So it is full of runtime branching, and it is full of runtime bitmask calculations that are necessary for setting the registers. And since these functions are long and complex, they will probably not be inline, so we potentially at least have the overhead of function calls as well. Now, if you look at these inefficiencies, the question that I want to pose you is, can we do something about it? Can we use C++ to get rid of them? The term zero-cost abstraction gets thrown around a lot in C++, but my question is, can we maybe do better than zero-cost abstractions? Or is C really as efficient as it gets? Now, to answer this question, we have to remember that this talk is about embedded systems. And what is an embedded system? It is usually a printed circuit board. Somewhere on this PCB, there is a microcontroller and a number of peripherals interfaced to this microcontroller. And there are copper traces running between the microcontroller and the peripherals. Now, this might not apply to every embedded project, but definitely to a vast majority of them. And if you look at a project like this, you probably also have the feeling that there is something inherently compile time about it. So copper traces are usually not rerouted magically during runtime. If it happens, then you have probably bigger problems. So when you are developing firmware for a project like this, you probably already know which pins will be used as GPIOs, which ones will be ADCs or part of an I2C communication bus. You probably already know the resolution of the analog digital converter. You know the frequency of your I2C bus. You know the address of the devices on the bus. So there are a lot of things that could and should be known about these kinds of projects at compile time. And if we are thinking about this inherent compile time nature of these projects, then these inefficiencies that we have just identified become unnecessary. And if you think about it from an applications point of view, every CPU cycle spent in the hardware abstraction layer is just a waste of time and energy. So luckily, C++ offers a lot of powerful and versatile features to deal with these kind of inefficiencies, while still keeping the flexibility of the hardware abstraction layer and also improving readability as well. So to prove the power of C++, what I did is that I implemented this project on a breadboard. It has an STM32 microcontroller on the middle, and it has 2 analog inputs. Now, in my case, these were just potentiometers so that I could set them by hand. But you can imagine that this could just as well be reading some kind of a physical value, such as temperature or humidity. As for the output, I hooked up some LEDs. So on one output, there is an LED array. It is handled by the GPIOs of the microcontroller, and it serves as a kind of a level indicator. And as for the other output, there is a single LED there controlled by a pulse width modulation signal. And you can think of this as a ventilator signal or pump control signal. My point is that even though this is only an example project on a breadboard, the application itself could still be some kind of a controller unit in a real-world operation. So what the firmware does is that it initializes the peripherals, and then it goes into the infinite loop. It reads the analog outputs, it sets or the analog inputs, it sets the outputs accordingly, and it measures the time for each iteration. Now, on one hand, I implemented this functionality with the provided hardware abstraction layer, and I used these modules for their intended purposes that I wrote there. And when I had this implemented, I started to replace the modules in the hardware abstraction layer one after the other with my own implementation that I specifically optimized for this inherent compile time nature of embedded projects. Now, replaced is not really a good word here because I didn't remove the unused modules. They were still present in the original hardware abstraction layer, but I extended the functionality with my own. And this is also very powerful because if I didn't know some aspects at compile time, or maybe they vary at runtime, then I can still go back and use the original provided implementations. Now, I also must add that these methods that I will show you are probably not usable in highly dynamic embedded systems applications, but they are also not unique to embedded systems. So I think that, for me at least, they are more apparent here because of this inherent compile time nature of many embedded applications. But these methods can and probably should be used in other areas of software development as well. So if there is something that could be evaluated at compile time, then probably it should. So let's look at these C++ features that I used to get rid of this runtime overhead. So on one hand, we have to talk about the C++ type system itself. It is very robust and it should not be underestimated. So for example, C++ enumerations, they are not plain integers anymore. There is no implicit conversion between the underlying integral type and the enum values. So it's much less error prone, and you actually have to give extra effort to introduce some kind of a bug into this type system. Now, another very powerful tool that we have are templates and concepts, because non-type template parameters allow for compile time parameter passing. So if you know some kind of a configuration or action that you at compile time that you want your project to make, then it probably makes sense to call a templated version of the function and pass this configuration as template parameters. And this is where concepts come in really handy, because as I've already mentioned before, concepts are a set of requirements that you can apply on template parameters. So if your template parameters are non-type template parameters, you can still use concepts, and you can put constraints on the values that you want to accept. So if you get an invalid value, for example, an invalid mode for a GPIO, then you will get a clear compile time error message. Another very powerful feature and very useful for embedded systems is immediate functions, because these functions are guaranteed to be executed at compile time. And I extensively use these for bitmask calculations, because if you already know what bitmasks we are going to use during operation, then it makes a lot of sense to calculate them at compile time, and then at runtime you can just simply, or the binary can just simply use the pre-calculated bitmasks. And if you use these in combination with concepts, templates, and fold operations, then you can calculate bitmasks even for example, a set of pins and not just a single pin at a time. So it's very powerful. Last thing that I want to mention is C++ 17's constant expression if statements, because these allow you to make decisions at compile time. So again, if you have the necessary configurations at compile time, then you can use these const if statements to not only to eliminate the comparisons and the jump instructions from your binary, but also the unused code. So the unused if statements are excluded from the binary as well. So it potentially also saves you memory space. Now, if we apply all of these methods to the code base, just go through them again one more time. So we use templates and concepts for compile time parameter passing and compile time parameter validation. We use immediate functions for shifting the otherwise runtime bitmask calculations to compile time. We use concepts if statements for compile time branching. And if we use all of these features in the code base, then the compiler will reduce these long and complex functions to only a couple of direct register operations, which will then use the pre-calculated bitmasks. So these functions will be much simpler than the original ones, and they will be more likely in line. So we potentially also save the overhead of pure function calls. Now, if we look at the results, they talk for themselves. So we have the original version and the improved version, and there is a huge difference in binary size. It's around 2 kilobytes. And if you remember, I didn't even replace all of the modules in the implementation. And if you remember, there are devices with as low as 16 kilobytes of flash memory. So if this application would get a little bit more complex, then this this difference could even decide if the application is going to fit into the flash or not. But the improvement is not only significant for binary size. We can see that in runtime performance, we save around 20% as well. So as you can see, the improved version or the new version could do 5 iterations now, while the original one did only 4. So it's around 30% increase there as well. So if we are talking about the overhead introduced by C++ abstractions, then code bloat is one thing that cannot be left unmentioned. In the previous section, I used a lot of templates to get rid of this inherent runtime overhead in the hardware abstraction layer. But the premise there was that some of these features, or most of these features, are known at compile time about the embedded project. Now, if this is not the case, if, for example, you have an oscillator configuration and you do not know it at compile time, or maybe it can vary during runtime, then it is probably not a good idea to use the templated versions of these functions, because then the compiler will generate a distinct function in the binary for every distinct specialization. So it will definitely increase both the binary size and the compilation time. Now, there are a couple of conclusions that I want to draw from this presentation and that I also learned by putting together this presentation. So the first thing that we have seen is that zero-cost abstractions work in embedded systems. They work even at the lowest levels possible, as close to the hardware as possible. We have seen that the abstractions introduce virtually no runtime overhead, and they also provide a lot of advantages, such as readability and maintainability. And for me personally, they also make development much more fun. We have also seen that our architecture of an embedded firmware matters. We often think about software architecture only as a way to organize code for readability and maintainability, but as we have seen here, it has huge implications on runtime performance as well. We have also seen that if certain criteria is met, so if you know, if there are aspects of a project that you can know about it at compile time, then it makes it possible to even go beyond the zero-cost abstraction principle of C++, and we can achieve a firmware that is highly optimized for runtime. And as a last thing, I just want to put my personal opinion out there. I think that C++ is very useful for embedded systems. For the future, I hope to see more support for C++ in the hardware abstraction layer, and in general in the embedded community as well. And I would encourage everyone to use more C++ for embedded systems whenever possible. Yeah, thank you for your attention. I hope that this presentation provided you with some knowledge as well. And if you have any questions, then feel free to ask them now, or you can also find me later in the hallway as well. Thank you.